Fellow mathematicians, we're going to take a look at everything that you need to know about first-order linear differential equations. We're going to go over how to identify them, how to solve them using an integrating factor, and then in the second part, a short proof of where the formula for the integrating factor comes from. Now, all of this starts from the basic form, what might be called standard form, of a first-order linear differential equation. And it has the following form. We have on the left side the derivative of y with respect to x plus a function of x times y, and then equals a function of x on the right side. Now, it's important to put your differential equation in this form for everything else to fall into place. And the way that you'll first identify if your differential equation is linear is with three simple checks here. So first, you want y and its derivative, dy over dx, or y prime, only raised to first powers. So think back through basic algebra and beyond, quantities that were linear were raised only to first powers. If there's a y squared in there, your equation is not linear. So that's the first check. The second thing to be aware of is for your equation to be in linear form, you want there to be a 1 in front of the derivative term. So in other words, in front of dy over dx, there should be only the coefficient 1. If there's some other factor in front of there, just go ahead and divide the whole equation by whatever's multiplying dy over dx. And once you divide the whole equation by it, you should now have it in linear form where there's a coefficient of 1 in front of the derivative. That's important because having a coefficient of 1 in front of the derivative will be how you identify p of x, which is used in the formula for the integrating factor. If there's another coefficient in front of the derivative, you're not going to be able to correctly identify p of x. So just be aware of that. And the third thing, the third check to be aware of, is you only want y and its derivative appearing on the left side. On the right side, there should be no y terms. So if there are any y terms, just move them to the left side and combine them and write it in linear form. All right, so always see first if all three of those are satisfied before you move on to those steps. Now, once you have your equation in linear form, you identify p of x, the function of x that's multiplying y, and p of x is used in the formula for the integrating factor, mu. And the formula is mu equals e raised to the integral of p of x. So it's really simple. Write your differential equation in this form, identify p of x, calculate the integrating factor, and then you can proceed with step 3 and beyond. Now, once you have your integrating factor, the first part in step 3, you're going to multiply both sides by your integrating factor, mu. But the key step is here in 4. You want to look at this left side as kind of looking like the end result of the product rule. At least this is how I like to teach first-order linear differential equations in my course. Why would this left side be related to the product rule? Well, you have the derivative of y plus some other quantity involving just y. Derivatives, adding, and the function, that sounds like the end result of the product rule. So briefly, this formula for the integrating factor, we use it because it's going to reverse the product rule. And again, we'll see this all come together in the proof in the second part. But right now, the key step here is 4. Once you've multiplied both sides by mu, the following always happens. The left side collapses or becomes the derivative with respect to x of the product mu times y, where mu is your integrating factor. And again, we'll see this all come together in the proof in the second part. All right, and once you do that, once you've collapsed the left side down to the derivative of this product, you just go to the last step, what I call the main idea of differential equations: cancel derivatives by integrating. So from there, you just integrate both sides, and integrating a derivative should cancel out. All right, now all the problems where we go through these steps in detail are going to be linked down below in the description, so check those out after this. But what I want to do is make sure that you really understand step 4 here, and let's go ahead and take a look at that with a really simple first order linear differential equation. All right, so first notice your differential equation is in linear form. You have the derivative of y with respect to x. There's a coefficient of 1 in front of it, plus something times y, and then you only have x's on the right side. So this is in linear form, and we can identify p of x, the quantity multiplying y, which here is the constant 3. So p of x is 3. And we go ahead and immediately go to the formula for the integrating factor, mu, which is e raised to the integral of p of x. So e raised to the integral, or antiderivative, of 3. And we're integrating that with respect to x. All right, now I want to point something out here, which hopefully your differential equations professor points out as well. That antiderivative, technically you can write it as e to the 3x plus c. Now that plus c that you get from integrating, you don't actually need it. So let's point out why. We're going to use some properties of exponents. I can rewrite that as e to the 3x times e to the c. Both e and c are constants, so this last term, e to the c, is another constant. We'll just call that c, and you can write this as a constant times e to the 3x. And just make sure you realize we don't need that constant in front, because if you multiply both sides by just the number, you can divide it off. We're interested in the part containing x. So you can basically always forget about the plus c in your formula for the integrating factor. You technically don't need it. So here, we're just going to say the integrating factor, mu, is e to the 3x. All right, so right now, we're all the way through step 2. Next, we're going to multiply both sides, and I want to emphasize multiply both sides because I've seen a lot of differential equation students, they forget to multiply the right side by mu. So always make sure, basic algebra, what you do to one side, do to the other. So we're going to multiply both sides by e to the 3x. All right, and the following always happens. This is the important step, step 4. The left side, that always collapses to the derivative of your integrating factor, mu, times y. So that should become the derivative with respect to x of mu e to the 3x times y. And the differential equation now takes the following form. This is our left side, so we have it as the derivative with respect to x of the integrating factor e to the 3x times y. And our right side is x times the integrating factor e to the 3x. All right. Now, right now, before we get into the second part, the proof of where the formula for the integrating factor comes from, let's just actually calculate this derivative using the product rule So you can see that this does go backwards above to what we have. All right, so this is going to be straightforward. We're just going to calculate the derivative using the product rule. Technically the chain rule as well, because of the e to the 3x term. And let's go ahead and calculate that derivative, just to make sure you understand why step 4 reverses using the product rule. All right, so let's calculate that derivative, differentiate the first term. That's where the chain rule comes in, 3 e to the 3x. Keep the second function, y, the same. Notice we have the 3 e to the 3x y term above. And then we add to that. Now you keep the first function the same, e to the 3x. But now you multiply by the derivative of the second. And we're going to write that as dy over dx. All right, and if you take a look at this expression here, that is exactly this, but with the order of addition reversed. We have e to the 3x times dy over dx, e to the 3x times dy over dx, 3 e to the 3x times y, 3 e to the 3x times y. All right, so that's how we end up using the integrating factor and reversing the product rule. Now, once you get it to here, it's really simple to solve. You just integrate both sides. Integrating the left side with respect to x, that's going to cancel the derivative. So we would get here the left side, e to the 3x times y, and we would just need to integrate the right side with respect to x. And that is typically how we go through the tricky steps here of using the integrating factor, because at this point, that just comes down to a Calc 2 integration problem. All right, now we're going to leave this one here. Again, the whole point was just to see the key steps, specifically step 4. Next, we're going to get to a proof of where this formula for the integrating factor comes from. And again, linked down below in the description, a whole bunch of problems on solving first order linear differential equations. Let's get to that proof. Next, we're going to see where the formula for the integrating factor comes from. Now, we're going to start by trying to look at the left side as being the end result of applying the product rule. And we might be applying the product rule to the derivative of y times some function. And we're going to figure out what that function is. That's what we're calling the integrating factor, mu. Now, in order for this to work, we might need to introduce an extra factor or function on that left side. So let's start. We're going to multiply the whole equation by an unknown integrating factor, mu. All right, we're going to multiply all terms by mu, including the right side. And what we would like to happen is that the left side can be collapsed to the derivative of y times our integrating factor mu, which again, we don't yet know what that formula is. We're working up towards that. All right, so let's go ahead and suppose this can be written as the derivative with respect to x. And I'm just going to switch the order here, the way it's usually written, and we're going to write that product as mu times y. All right, now in order for this to happen, in other words, these terms being able to be collapsed back to the derivative of the product mu times y, let's go ahead and see what mu has to satisfy for that to be true. Let's go ahead and calculate the derivative here using the product rule. And then we'll compare that with what's above to get a very simple equation to solve for mu. So here we're going to apply the product rule. Very straightforward. We're going to differentiate the first function, mu. We'll write that derivative as d mu over dx. That's going to multiply the second function. And then we add to that the first function, mu, times the derivative of the second. The derivative of y, we'll write that as dy over dx. All right, now to make this as obvious as possible, let me just switch the order of addition, and we'll write this as mu times dy over dx plus d mu over dx times y. All right, now again, if this is going to work, these terms should be the same as what's above there. Now we can compare. We have mu times the derivative of y, mu times the derivative of y, and we have a y term, but some of the other factors look different. In order for this to be true, in order for that to happen, what we must have is the quantity multiplying y here, which is the derivative of mu with respect to x, that has to equal the quantity multiplying y above, which is mu times p of x. And that gives us a simple differential equation that we can solve for mu. Let's go ahead and write it down. We have the derivative of mu with respect to x has to equal mu times p of x. Let's write that down. So we get the derivative of mu with respect to x has to equal mu times p of x. And that is separable. All right, so let's go ahead and divide the mu term to the left side, and we'll multiply dx over. We'll write this as 1 over mu d mu equals p of x times dx. At this point, it's separated, so we just integrate both sides. Integrate the left side with respect to mu, and integrate the right side with respect to x. The left side is going to integrate to natural log of mu. And because we're not specifying a formula for p of x, we're going to leave the right side as the integral of p of x. And our last step to get an explicit formula for the integrating factor mu, solve for mu here by exponentiating both sides using base e. And what we get is mu equals e raised to the integral of p of x. And there we go. Now, your differential equations course might be going through how you use the integrating factor slightly differently. You might be using differentials, but it's all equivalent. In my differential equations course, I like to look at this left side as being related to the product rule, and it all falls into place there from basic calculus. All right, now if you're looking for some problems to practice with these steps using integrating factors for first order linear differential equations, the problems are linked down below in the description, so check those out. Hope you enjoyed the content. I hope you're learning a lot in your differential equations course. If you are, support the channel, like and subscribe.